With 34.2 million people, almost 10.5% of the United States facing diabetes daily, there is a global demand for insulin. However, the price of insulin continues to soar, especially in the United States, where the cost of one vial of insulin went from just $21 in 1999 to $322 a vial in 2021. It is clear that the current insulin market makes such a life-saving medicine unaffordable and inaccessible. The Algae to Insulin project aims to reduce the cost of insulin production by genetically engineering a strain of algae called Chlamydomonas reinhardti to produce mini-proinsulin, a protein with the potential to fold into insulin. So how do we plan to get algae to make insulin? First, we will assemble the genetic construct of our recombinant plasmid using a common ligation method called the SLIC method. Once ligated, our plasmid contains necessary promoter sequences, mini-proinsulin as our gene of interest, and various other genetic sequences required for homologous recombination into the chloroplast of our algae. Next, we will then insert our plasmid into E. coli using heat shock transformation to rapidly amplify our plasmid. This will in turn increase insulin yield in later steps. Then, we will lyse the E. coli cells, harvest our recombinant plasmid, and use the glass bead method to reintroduce our plasmid into the genome of the chloroplasts of our algae. Lastly, we will lyse our algal cells and then purify our insulin protein using a form of chromatography called immobilized metal affinity chromatography. So why did we choose C. reinhardti? Because C. reinhardti is a photosynthetic organism, it only requires minimal inputs, including sunlight, low filtration grade water, an inexpensive buffer, trace minerals, carbon dioxide, and a nitrogen source. With minimal input, a liter of C. reinhardti costs as low as 1 cent per liter of media to culture. 1 cent compared to the $200 per liter it costs to culture CHO cells. Even for cheaper organisms like E. coli, media prices cost downward to only $4 per liter, but they are limited in the type of human proteins they can make. If we successfully transform Chlamydomonas reinhardti to produce insulin, future research can apply similar concepts to produce other medicines. If successful, Algae to Insulin has the potential to transform medicine into something more affordable and accessible, the way it should be. I'm Shannia De Leon, currently studying biotechnology at the University of California, Davis, and this is Algae to Insulin.